So in this video, I'm going to talk a little bit about the perfect or ideal gas. The perfect or ideal gas, well, which really doesn't exist. But if it did, the gas particles themselves would have no forces of attraction between them. The gas would be completely compressible to a zero volume, and the gas particles would exert pressure on the insides of their container. The formula for the ideal gas law is that the pressure times the volume equals the number of moles times R, the ideal gas law constant, times temperature. So now that you know a little bit about ideal gases, which one of these does not describe an ideal gas? Hopefully you said number 3, those strong intermolecular attractions. The gases are going to bump into each other and the insides of their container. That's what creates pressure. The ideal gas would take up zero volume, and each of the particles, while we can talk about the average speed of those particles and get the temperature, the individual particles would be moving at different temperatures. All right, so let's do some ideal gas law practice. An ideal gas law problem might look something like this. What is the pressure exerted by 1.8 grams of hydrogen gas in a 4.3 liter balloon at 27 degrees Celsius? And so the first thing you want to do is take a look at your ideal gas law, and then take a look at what you've got in your problem. So we've got grams of hydrogen gas. So that's not pressure, volume, number of moles, R or T, but we can get the number of moles from grams. Then we've got 4.3, which are liters. That's going to be our volume. And then 27 degrees Celsius, which is our temperature. We just need to convert that temperature to kelvins by adding 273. So take a second, see if you can substitute those in. This is another plug and chug equation. So see if you can plug those values in and solve for the pressure. All right, so first I've figured out my number of moles of hydrogen gas. Then I plug those variables, those factors, into the equation. I've got my temperature converted to kelvins, and then I simply solve for P. So take a look. Did you get 5.2 atmospheres? If not, I do believe we have another one. So the biggest problem with the ideal gas law and all of the individual gas laws is that figuring out which formula to use when. So if you have two pressures, volumes, and temperatures, you'll want to use the combined gas law or one of the other gas laws, Boyle's, Charles, or Gay-Lussac's law. If you only have one pressure, temperature, and volume, or you have number of N's or number of moles or grams, use the ideal gas law. Of course, if you're asked about partial pressure, use Dalton's law. All right, so which law or equation would you use for this one? Take a look at it. Hopefully you were thinking Dalton's law of partial pressure because it's asking for a total pressure, and it's giving us the pressure of oxygen and the pressure of nitrogen, two separate gases. So let's take a look at this one. Which gas law would you use for this problem? Hopefully you were thinking Boyle's law because you have pressure and volume and pressure and asking for a second volume. How about this one? Hopefully you were thinking Charles's law because we have, it gives us pressure, but notice the pressure is constant. And so that's how I can tell that it's Charles's law, because I have temperature and volume. And of course, Charlie Brown is a TV show, so I remember that as Charles's law. How about this one? Hopefully you were thinking the ideal gas law, PV equals nRT, because it's asking for the number of moles. We know the volume, we know the pressure, and we know the temperature. How about this one? Hopefully you were thinking Gay-Lussac's law, P and T, because we have the pressure. The temperature is at 250 degrees. And then, of course, dropping to 170. And that's one of those problems with flights that does occur. All right, once again, don't forget that you do stoichiometry with gas laws, with gases. And you've always got this equation or this relationship, this ratio, fraction style ratio, conversion factor is that 22.4 liters of a gas at standard temperature and pressure is equal to 1 mole. So how many liters would be required to produce 20.3 grams of water? And there's our equation. I apologize, it's on 2 lines. Hydrogen, 2 moles of hydrogen plus oxygen equals 2 moles of water. So take just a minute and figure this equation out. Figure out how much oxygen in liters are required. And then I'll give you the answer in just a second. And so the answer, after converting my grams of water to moles of water, my moles of water to moles of oxygen, because we have a 1:2 ratio, my moles of oxygen to liters, 12.6 liters of oxygen are required. Here's another one. What volume of HCl gas at STP would be generated if 10.2 grams of NaCl react? So now hopefully you took those 10.2 grams of NaCl, used your molar mass to convert to moles of NaCl, used your mole ratio from the balanced equation that 2 moles of NaCl equals 2 moles of HCl to find your moles of HCl, then use the relationship that 22.4 liters equals 1 mole for a gas, and hopefully you came up with 3.90 or 3.91 liters of HCl needed to react there. And that's all we have for wrapping up the gas laws. I hope this has been helpful.